So good morning, everyone, and welcome to the ELIXIR Czech Republic Friday Coffee, which is a series of seminars dedicated to tools and resources, which is part of the ELIXIR Czech Republic infrastructure. Today, we have a special guest from Palacký University, Olomouc, and Pavel Polishchuk, I think Maria Matveyeva, will tell us a bit more about the QSAR models, which are used in a structural and physicochemical interpretation of the molecules. So Pavel, floor is yours.
Thank you. Thank you for the presentation. So today I would like to show you our tool, which we started to develop several years ago, and now it's becoming more and more mature. And this tool is specialized for interpretation of QSAR model, but not only. So I will show you this pipeline, and we implement this pipeline in one-button application. So it can be used even by non-experienced users, because you just need to click one or two buttons, and that's all. First, what I wanted to say is that maybe all of you or majority of you know what is the machine learning and QSAR modeling. So we have some structure, calculate some descriptors, and then we will use some machine learning methods to find the correlation between those descriptors and a particular property or endpoint. And these machine learning models quite frequently considered as a black boxes. And my opinion is that it is not true, and every model can be interpreted. So we can retrieve from every model some useful information which can be used for different purposes. The main purposes of interpretation of those black boxes are knowledge-based validation of models. So this can be used like an additional layer of validation to increase the trust, your trust, and other researchers to this model, because interpretations should somehow correspond to the knowledge of experts in this field. And if it retrieves some contradicted knowledge, then that's a question. Or the knowledge of experts is not complete, or the model is wrong. And the second option, if we know some favorable or, for example, less favorable fragments, moieties, properties of molecules, we can use this information for structural optimizations. For example, we know that some groups are favorable, then in our optimization study, we will not touch them, and we will touch other groups in our molecules. And how we can retrieve this information from models? There are a lot of approaches which can be applied to retrieve this knowledge. There are really a lot of them. Some of them are, or even almost all of them are specific to particular descriptors or machine learning methods. But there are a group of approaches which are agnostic to descriptors and machine learning methods which were used to develop these models. And one of these approaches is a universal interpretation approach, which we proposed quite a lot of time ago. And here is just a brief concept how it works. So if we have a molecule A and we want to estimate the contribution of some group, in this case piperidine, we can remove this fragment from our molecule, calculate predicted property value for the initial molecule and for the molecule after removal of this fragment of interest, and calculate the difference between these two predicted values. And this can be interpreted as a contribution of this particular fragment in this particular molecule. So that's very easy, and this scheme does not rely on the understanding or structure of a model, descriptors which are used, so it can be applied to almost any kind of models you have. I mean QSAR models, of course. And we developed and implemented this approach in our standalone software and later in web-based web application. I will show you how it works in a standalone software, which was written in Python, because it has more features. All software are available from they're all open source. They're available from GitHub. I will provide you the links at the end of the presentation of these repositories. And at their pages, GitHub pages, you can find other useful links. So just start SPCI and it will start the Win graphical interface. So I hope you see, so it's not so small, these letters. So here we should choose our model, our SDF file, which contains structures and property values. In this case, we will perform these examples on a data set of compounds and their permeability through blood-brain barrier. So we can choose it. We can choose which field contained our property value. So we will model permeability as a classification task. So class 1 is a permeable, class 0 non-permeable. Then we have to choose descriptors, which we can use for modeling. First two cases are more demanding from the computational point of view, but they can give you more information. I will show you this at the end of the presentation, but for beginning, you can use some standard RDKit descriptors, for example, like Morgan. They can be count-based or binary fingerprints, it does not matter. Then you can specify how to name your compounds, and then you have to choose which model to build. So binary classification or regression models, and you can choose which models to build. Then just press a button, build models, and you can see that there is something started to happen in console, and it should be pretty fast, I hope. Let's back to the, yes, here we will see. So with SIRMs, these are special kind of descriptors which are quite similar to RDKit descriptors, so it's also substructural fragments, but there are some additional properties that those atoms in fragments can be labeled by their properties. For example, partial charge, lipophilicity, refraction, molecular refraction, hydrogen bonding, ability to form hydrogen bonds, and so on. And this adds some more information to the model, and we can also retrieve this information from the model. So yes, first group of models. This, what happens behind? So behind, all models built using the cross-validation. So based on the cross-validation approach, all tuning parameters are tuned. So it automatically chooses the best model and according to different tuning parameters available for every model. For random forest, it's the number of trees and the number of variables. For SVM, it's also C value and oh, I don't remember the second one. So it uses just ordinary grid search cross-validation, which is implemented in Escalon. So this is somehow similar to recently represented Galaxy project, Galaxy platform, but here it was implemented as a just one button application. So all these scripts which are behind this graphical interface are available from console, and it gives you much more flexibility if you need it. But if you just need to build a model and get some contribution of fragments, you can use graphical application or our web-based application, which I show you later a little bit. So probably my computer is a little bit slower because it's too heavy loaded with other applications probably, but it should be faster. Sorry for that, but we need to finish it. Yes, here it also printed in console, and we'll show the statistics later. So these are balanced accuracy, specificity, sensitivity, and kappa values. And here is tuning parameters which were used to build this particular model. And those models can be used for prediction of your external test set if you need, or prediction of new compounds for virtuous linear also, and it is all available through the graphical interface on the tab of Predict. So we are almost close to the end, so the final models are evaluated. So after the tuning parameters were set up, the final model is built on the whole data set using these selected parameters. So all models were built, and if you click the button Show Statistics, you can see the same values which I show you in the console. So balanced accuracy, sensitivity, specificity, kappa value, and those optimal parameters which were used to train this particular model. So that's quite easy. So we can switch to the second tab. Okay, what happens? Why it does not switch? That's for the first time. Okay, we can interrupt it. That's strange. Okay, we can just restart application. The good thing is that you can reopen the same project which you already created. So you can just need to select file, select again those descriptors, models, and switch to the second tab. And here you can use and choose different fragmentation schemes. There are several ones. Default fragments means that it will calculate the contribution of widely and commonly occurred functional groups and ring systems. Murka scaffolds, it means that it will calculate the contribution of Murka scaffolds in each molecule. There are some automatic fragmentation which is quite exhaustive and which will produce you a lot of data, but there are also, you should understand how to analyze this data, and for beginners it can be quite tricky, but for more experienced users I believe that it will be very difficult to understand how to analyze and retrieve data which would be useful for you. You can also supply the fragments of your interest, and the program will search for these particular fragments in all your molecules and will calculate the contribution of these fragments to you. Or you can calculate contribution of every single atom. It is also possible. So in this scheme, it does not matter how large your fragment. It can be just one atom as well. And this sometimes it is more useful and more convenient for visualization of results if you can calculate the contribution of atoms, which can be easily visualized. So we'll use the default fragmentation scheme because it is just faster, and will provide you already some interesting results. So it searches for fragments in every molecule, then it calculates the descriptors for new molecules obtained by the removal of these fragments, and calculates the prediction and calculates the contribution. So it's very fast and calculation is completed. Just a few seconds. Okay, so what we can do next? We can visualize by using this graphical interface as an option, but we have RDKit implementation, which is more rich in features. Here you can specify what kind of contribution you want to depict, just overall contribution, which models, and just show in the window, not save to file, and the minimum number of occurrences of fragments you can specify to eliminate some rarely occurred fragments. Just click a button plot, and here it returns you does not. Oh, no. Yeah, in this case it's, and it returns you the information, some aggregated information for your data set, the whole. So it summarizes the contribution of identical fragments across different molecules in your data set, and then provides this information as a box plots for individual models, GBM, random forest, SVM, and consensus, which are means just averaging of contribution of individual models. Here they are ranked according to the overall consensus contribution, and you can see in this case that, for example, presence of a 3-fluoromethyl group is considered as favorable for permeability through blood-brain barrier by the model. For example, also presence of piperazine or piperidine rings is also favorable, and contrary to that, presence of carboxylic acid group, thiazole, amide group, or nitro group wouldn't be favorable. So it's quite logical and it corresponds to the expert knowledge. So in this way, you can just obtain general information. It also can be useful for further optimization, but you can also look inside the text file which is created and analyze per molecule these contributions. And how to interpret this further? The interesting thing that in some cases you can see quite large distribution, quite wide distribution of those contributions, and it means that in this case the contribution is highly dependent on the chemical context of this fragment. So it means that carboxylic acid group, its contribution depends on the on which fragment this group is attached. But it is not the case of a 3-fluoromethyl group. So in this case, it doesn't heavily dependent on the chemical context. And we developed also special tool and implement this in Rspca package. This is our R package which helps you to analyze output of this software, because it has more options how to rank, sort, filter, visualize these molecules and analyze them. And I will show you a little bit advanced analysis. So we can try to retrieve information about the context of those fragments. And we also automatize this pipeline. So we just load our contributions, then add full names just for clarity and convenience, filter and remove some rarely occurred fragments based on the default parameters, but you can specify your own. Then just select fragments and their overall contribution in a consensus model. And then we just apply option function cluster all, which perform clustering of contribution for each individual fragments. What does it mean? So we used Gaussian mixture model and we try to identify whether this contribution of fragments consists of one Gaussians or several Gaussians, which we consider like a clusters. So it's one-dimensional clustering. In some cases, the contributions are not separated, so they're quite close to normal distribution, for example, and described by single Gaussian. In some cases, like in carboxylic acid group, you can see that there are some different Gaussians and different distributions. So there are several contributions which are close to zero, and there are several quite negative contributions. And further, you can retrieve this information, which molecules belong to each cluster, calculate some additional data, retrieve some mean or variance of those clusters, and then, based on their molecular names, you can retrieve and look on those compounds which corresponds to each cluster. And here you can see that, for example, aspirin, which is not permeable, and carboxylic acid group in this case has quite a high negative contribution, and it means that removal of this carboxylic acid group can make those compounds permeable. Not necessary, but can make. The same for cetirizine compound drug. So in this case also carboxylic acid was captured by a model like an unfavorable fragment. And if you want that this compound will permeate through blood-brain barrier, maybe it's better to somehow mask or remove this group from your molecule. In the opposite case, where the contribution of carboxylic acid group is low, for example, close to 0, in those compounds, the first compound is already permeable, and the effect of this carboxylic acid group is not so important in this case. So the model captures that in this case, the carboxylic acid group is not very important. Another example is cefotetan. These are very complex molecule, and again, the model recognizes that this single group is not important for permeation through the blood-brain barrier. And I think that it is due to the complexity of this molecule. And there are a lot of different groups which can be also unfavorable. So here is a tetrazole moiety, amide moiety as well, and those ring systems also. And it is not permeable, but due to this complexity, this group is also not recognized. So for optimization, maybe it would be more useful to retrieve contributions for every fragment or every atom and analyze them in more details. Here I just briefly show you the what can be done and how this can be analyzed and interpreted. And the last thing, yes, I have a few minutes, is more advanced interpretation of those results. So if we represent molecule by descriptors which can encode separately partial charges, lipophilicity of atoms, hydrogen bonding, and so on, we can interpret fragments in terms only of these particular groups of descriptors. And when we remove this fragment from the molecule, we can remove it only in terms of a single group of descriptors. In this case, HB means hydrogen bonding. So we recalculate descriptors for hydrogen bonding and keep all other group of descriptors as is for the initial molecule. And then the difference between these two predicted values will designate the contribution of this fragment in terms of their hydrogen bonding propensity to the property. Yeah, it's maybe a little bit tricky, and I will show you how it looks. Yeah, this one. Here is just how looks the web interface of our application, which is available by the address SPCI IMTM-CZ. You can upload your SDF file, and you can again build the model and perform the interpretation, but it will take more time because they use those series descriptors which are property labeled with different properties, like I mentioned, partial charge, lipophilicity, and so on. So we will not do this now. So we just open this file like a project, and we can see here the statistics of these models which were built. We can download the pre-calculated already contribution for default fragmentation scheme, and those downloaded file we can open in our not incorporated in this web application web page. It's a separate server which can be used for analysis or visualization of those contributions. Here you can just select, yeah, we can use this file, this would be the same. So it will automatically calculate on the fly and depict these contributions. But I wanted to show you the contribution based on different properties. So yeah, that's all. So here we just depict contribution in terms of different atomic properties like electrostatic, which is modeled by the partial charges, hydrophobic, which is modeled by lipophilicity, hydrogen bonding, and dispersion. And here you can see that, for example, negative contributions of those groups like carboxylic acid, nitro group, and so on, they are mainly due to the unfavorable hydrogen bonding pattern. So, and this can be interpreted in this case that ability to form hydrogen bonding for these groups are unfavorable. And if you will be able to somehow remove this ability, for example, methylation of those carboxylic acid or amide, this can be improved. So these are just additional level of interpretation. I think it is more advanced and it's not so frequently used, but it also can provide you some additional insight in your data, which is available. So that's all what I wanted to show here. At the end, I just wanted to show that we have repository, SPCI repository, which implement all these calculus scripts and graphical application. We have complementary Rspci repository, which is a R package, and which implements a lot of functions for analysis of those data. And we have this web-based application, which is just started to develop. So we have to incorporate here is the visualization, which is the most difficult thing, I would say, because for different projects, you need some different ways to analyze this data, and that's why it's difficult to find some common visualization approach which would be suitable for multiple cases. And here you can also see these links. So if you are interested, you can go by these links, and in these repositories you can find the relevant citation and references. So this is also from my side. So thank you for your attention, and if you have questions, I would be glad to answer them.
Okay, Pavel, thank you very much for your lecture. We have few questions. So Karel is asking, I see SD as a starting point. Is it possible to use smiles?
In this case, no.
No.
At least this software uses only SDF.
Yeah, Vojta is asking, how big is the data set you use for the demo?
For this case, I used relatively small. It contained just 350 molecules. But if you run this software on your own computer, you can use any size of a data set. But on a web-based application, as I remember, there is a limit on 1,000 molecules.
Mm-hmm. Okay, Karel again. What is the difference between M and N value for individual fragments? Number of molecules with individual feature within the dataset, they seem identical.
Yeah, in that case, that was a bug of the software. So, yeah, M is the number of molecules which contain this feature, and N is the total number of features in a whole data set. So if a molecule has several such features, the N number will be greater than M. Mm-hmm. But unfortunately, due to this bug, you see just N values, I believe so. But we will fix this. So I also noticed this bug, so yes, we will fix them. I just didn't want to touch them before this presentation.
Okay, okay. Stan Mazurenko is asking, are the overall contribution you showed related to Shapley shape values in any way?
Shapley values, we don't use Shapley values, so these are something different, because Shapley values, they calculate contribution of individual descriptors, and here we calculate the contribution of fragments. And Shapley values cannot be applied for models, for example, if you use uninterpretable descriptors, and these are limitation of those specific approaches which can be applied only for particular type of descriptors. So Shapley values, okay, you can calculate this for any descriptors, but if the descriptors and non-interpretable, that is not useful. So for example, some autocorrelation index and so on. But if you use some interpretable descriptors like fragments, yes, it can be done in similar way like for Shapley values. I hope that I answered the question.
Pavel, last question. Did you publish or did you perform any kind of study with the results which are in some sense new regarding the previously used methods? I mean, did you demonstrate the performance of the tool you just introduced on some concrete case?
Yes, there are. I will just show you here in the presentation. I provide, and these links are also available in GitHub repository. So we published the paper 4 years ago, where we demonstrated on different data sets how it can be applied. And we recently submitted to the Journal of Chemoinformatics publication where we developed some synthetic data sets with predefined endpoint values for particular features, and then we built a model and tried to retrieve these features by model interpretation. And we also demonstrated that this approach is applicable and is able to retrieve those features captured by model, and those features are relevant. So these are features the same which we use for design of this data set. So I hope that soon this paper would be published, but it is available as a preprint, and I can share this link if you are interested.
Okay, so probably another question: if you are approached by, let's say, the experimentalist, the chemical synthetics, or some other field, are you willing to collaborate, or actually better like offer your software or use the kind of the training for the people who are interested?
Yeah, well, of course, we can collaborate. So if people are interested in this approach, they don't want to go too deep in this interpretation approaches and those tweaks and others. So we are open for collaboration, and we would be interested because I believe that the power of this interpretation of machine learning methods are underestimated, because mainly when we talk about some optimizational study, people prefer some structural optimization. And I understand this point because you can obtain more explicit knowledge of how this molecule binds, and you can think how to optimize them. But those machine learning methods, I think, would be most useful for optimization of some ADME properties, where you cannot build structural models. And in this case, this can help you to guide your optimization. So define some favorable or less favorable fragments, and then somehow to use this knowledge for optimization of those molecules.
Okay.
So yes, I'm open. So
thank you for all your answers. Thank you for the seminar. And if anyone is interested, you probably saw the email for Pavel, so don't worry and call him or contact him. And see you next Friday. Have a good weekend. Bye-bye.
Okay. Thank you. Thank you. Have a good weekend.